Okay, so today I want to do a little bit of a recap um, of this uh, generalized optimal detection schemes that we have been looking at. Um, the reason I thought of doing this is because when I asked you last time about how to connect the some of the more uh, improved schemes for beamforming or for chord division multiple access reception, how to connect it with the single user mesh filter. I thought that most of you kind of struggled with that. So I thought that I will maybe draw some block diagrams to kind of clarify what is the connection between the single user mesh filter that we have studied even in CT516, where the single user mesh filter was actually the optimal detection scheme, and how that SUMF, single user mesh filter, does not remain optimal scheme when these basis functions are not orthonormal. And then what can we do to kind of improve upon single user mesh filter? We looked at the decorrelating scheme, that is one scheme, and the MMSE scheme was the other scheme that we have seen. These two are by no means the only two schemes. There are many other schemes as well, but let us kind of put in some context the connection between the SUMF and the decorrelating detection and MMSE. So that is my purpose, at least at the beginning of this lecture session. After we complete this, I want to go over a few papers that are written currently on the topic of massive MIMO, on the topic of millimeter wave communication, very much the 5G technologies that are being explored as of today. And we will see how what we have been doing, what actually you are doing right now in your lab, and what you will be doing in the next lab, how that all connects with the 5G research. So let me begin right away. So we have studied these three different receiver structures, and we have seen that they are applicable in a variety of different application domains, although we have looked at currently only two application domains. One is either the spatial filtering, which is the beamforming, or temporal filtering, because the main message of the previous set of lectures was that the temporal filtering and the spatial filtering have a great connection, have a great analogy between them. In fact, the mathematical models are identical. So if you learn how to do temporal filtering, then you can also do spatial filtering or beamforming, or vice versa. And so that is one application domain that we are considering, the topic of beamforming, which is a very important and relevant technology in today's world in context of 5G. And that is because at millimeter waves, which is the frequency band which is being considered for the next generation systems, the model that we have seen of uniform linear array is largely applicable. And so The beamforming for MIMO is it's a very relevant application. If you do good work in MIMO beamforming, then you can actually just jumpstart your career like anything. You will be, you'll get a very good, you'll get a position at some very good university, not only within India but abroad also. And also, if you make your name, I think there'll be no shortage of big companies willing to hire you. So beamforming, millimeter wave, MIMO, all of these are today's terms. I think they carry bigger bang for bucks compared to even machine learning and AI, because everybody and his brother today is focusing on machine learning and AI. The nice thing about this is that it's a very kind of specialized domain, which actually requires you to do a lot of machine learning algorithms. The two algorithms that we have looked at, the decorrelating detector and the MMSE detector, and also the eigenanalysis approach that you have considered for your lab, the MVDR algorithm. All of this, as I've been, I think, repeatedly saying, they are derived from machine learning literature, in fact, and they have application in that domain as well. Whereas what you are learning through this course is how to apply this advanced ML/AI/DSP techniques. Basically, it's linear algebra math. How to apply them to some very concrete application areas which are relevant today, which are these 5G areas. And so if you get a very firm grip, if you are very solid in the conceptual foundation of these techniques, I think you will have this skill set, you will have expertise, you will have knowledge, a kind of a deep understanding that not many people have, I think, to be quite frank. So in some sense, this is kind of best of both the worlds. You are not only getting a good conceptual foundation and conceptual strength of understanding, not only for in the communication domain, but also these algorithms are generally applicable outside of communication area. So these are the three algorithms that we have seen, and we have applied them to the beamforming techniques. So as I was saying at the beginning, that let us look at the block diagram representations so that we can kind of put these different algorithms in a proper context. And also, I mean, if some of you are thinking about, let us say, doing some FPGA implementation of MIMO techniques, then these diagrams that we'll be looking at kind of give you some very high-level picture of what the implementation schemes would look like. These diagrams are going to be focused on the beamforming application. But recall that the CDMA reception techniques that we have looked at have a very close mathematical connection with the beamforming. And so although we are going to be talking about this in the context of beamforming, with only a very slight shift in your mindset, you will be able to kind of just carry this conceptual diagrams forward and apply them to the CDMA or the non-orthogonal multiplexer schemes as well. Okay, so now the first diagram that we will be looking at is the one that okay, yes. So yeah, these diagrams are written with the perspective of implementing these three techniques. it will be, I think, useful and interesting for you to see how to extend this diagram so that they can represent the direction of arrival techniques or the frequency of arrival techniques that you are currently studying. So please spend some time on that also, apart from just understanding what I'm going to show to you. See if you can extend your understanding to this DOA, FOA problem as well. Okay, so this is the very first diagram that I think we have seen in one of the earlier lectures. This is just showing the uniform linear array. There is some RF wavefront which is impinging on this array at some angle theta, and it takes some time t of s to propagate from the first element to the second element and so on. And in the context of beamforming, we have seen that this t of s, which is the delay the waveform takes, the extra time that the waveform takes to go from one element of the array to the other antenna element, it can be written as a function of the spacing between the elements, which is denoted as d, and the angle theta. Who remembers that formula for t of s?
Sin theta by c.
Joel, you are not audible.
So let d be the spacing between two arrays.
Yeah, d is the spacing between the antenna elements of the array. Yes.
Then d sin theta by c.
Yes, correct. So t of s is d sine theta divided by c. I mean, obviously, if this was a diagram of the FIR filter, then this t of s is nothing but the sample duration. But here, let us continue forward with this beamforming perspective. The output of these different elements are multiplied with some complex valued coefficients. These are known as the beamforming coefficients. They collectively make the beamforming weight vector. And then what we get is the beamformer output. We can also think of this diagram in a little different manner, where we will say that because of that d sine theta divided by c, the signal, which is assumed to be a narrowband signal that has been transmitted by some particular transmitter, which is located at some angle theta with respect to this uniform linear array. So that signal, by the time it reaches this different antenna elements, gets multiplied by these different coefficients. And these coefficients are together defining the complex exponential vector at certain frequency that we have called f naught in our earlier lecture slides. And that f naught is actually is defined as the spatial frequency, and it turns out to be sine of theta naught divided by 2. That is how we have defined the spatial frequency. So once we define f naught as sine of theta naught divided by 2, then this set of multipliers together define that complex exponential vector. This we have seen way back, I think almost toward the beginning of the semester. All that I have done is I put it in terms of explicit complex valued multiplication of the transmitted signal that happens by the time the signal reaches these different array elements. And then this bottom part is the same as before, same as what is on the previous slide. But with this, what you can say is that we have a vectorial representation of signal at the output of these different elements. And we can think of our beamformer also as a vector of beamforming coefficients. And the output of the beamformer is nothing but the dot product between this vector here, which we can call the propagation vector or array vector or array signature vector and so on, with our beamforming vector. And the result that we get is the output of the beamformer. Okay, so once we make this type of diagram, we will kind of abstract it out and just write it as some beamforming scheme that is happening, which is essentially the dot product. We don't need to look at the detailed implementation, which is fairly simple. You are just doing complex valued multiplies and then add. It is this vector which actually determines the characteristic of the output of the array. And this characteristic output is completely determined by the angle of arrival of this particular transmitter, theta naught. And so sometimes in the array literature, this vector, which is called array vector, is sometimes also called the spatial signature vector. The reason it is called a signature vector is because if you look at the particular output of this ULA, you can almost see a signature. That signature is this theta naught, the angle of arrival. If the angle of arrival changes, only thing that changes is the argument of the complex exponential. Everything else remains the same. So the characteristic, the signature, is the DOA or the AOA, the angle of arrival theta that we have defined earlier. The reason I wanted to bring it out is because just like this is called the spatial signature vector, we have also seen the signature sequences. Also, maybe we have called it the spreading sequences in context of CDMA. In CDMA, as we saw last time, these multipliers are not applied by the propagation channel. They are not applied by the wireless communication channel. They are instead applied by the transmitter itself. And they are not complex exponential values as a function of the angle of arrival. They are instead just sometimes BPSK chips, minus ones and ones. But those chips are unique to a particular transmitter. And so there it is in the CDMA context, something quite similar is happening. And there, instead of denoting or calling it as the spatial signature vector, it is just called the signature vector for a particular CDMA transmitter. And then what we have done here within this block is not then obviously beamforming, but it is called the match filtering operation at the CDMA receiver. It is a single user match filter. And the single user match filter, all that it does, as we have seen here, assuming that the receiver knows the direction of arrival, which can be estimated using the algorithms that you are implementing as a part of the currently ongoing lab. So assuming that the receiver knows the direction of arrival, it will make the beamforming weights to be just complex conjugate of the array vector weights. And so that is why this is called the match filtering. And this is called the single user match filtering, because all that we are considering is that there is only one user present in what we are receiving. Okay, so this is the single user match filter version of the beamformer. And this we have actually seen in a lot of depth in the earlier lecture, we have seen that when our DOA is estimated perfectly so that this is indeed the case, the beamforming coefficient is just directly the complex conjugate of the array vector, then all of these lines become 1. This W conjugate W is always 1. Because remember, this W is a complex exponential function. Only thing it has is the phase. Its magnitude is always 1. And so if you take any complex number whose magnitude is 1, and if you multiply that complex number by its complex, the value becomes 1. And so each individual line gives you the same value of 1. And so at the output, you get the maximum output, which is equal to capital N. That is the characteristic of the single user match filter, that it will maximize the output in the direction of interest. Also, so that in case of suppose this transmitter is not exactly where the receiver thinks it is, receiver thinks that the transmitter is at some angle 60 degrees, let us say, and so accordingly it defines this single user match filter weights. But it turns out that the actual transmitter position is 55 degrees. Then there is a mismatch. This beamformer is no longer the matched filter. There is a 5 degree of mismatch. And we saw that once we convert that 5 degree of mismatch into frequency mismatch, that earlier on at some of the initial lectures, we called that as small delta f naught. Then the output becomes sinc function of that small delta f naught. And that sinc function and its characteristic is what we have studied earlier on. So this match filter, why it is optimal, why it gives the maximum output for the desired transmitter, and why it kind of gives increasingly lower outputs, why it essentially performs filtering. In this case, it performs the filtering in the space in the direction of arrival domain, is what we have studied at a great length earlier on. So this is just diagram of that mathematics that we have looked at. Okay, now we will, just the way we abstracted out the beamforming operation as just doing a vector dot product, let us abstract out the channel effect, the array vector effect, and just make it call it some array vector for transmitter 1. What that array vector is depends on the application that we are looking at. If you are looking at the beamforming, then that array vector is a complex exponential vector. If you are looking at CDMA or NOMA, then this array vector will be the signature sequence. In this set of lecture slides, what we are focusing on is that the received signal may not have only contribution from one transmitter, but it may have contribution from two transmitters. Well, then what we can say is, one simple thing to do is to do single user match filtering for transmitter 1, which is this dot product, and then put another algorithm within the same FPGA, which will do the dot product for user 2. And here again, we are assuming that we somehow know the direction of arrival for user 1 and user 2. And so we get basically an extension of the single user match filter. Now we can say that, well, maybe not 2, but maybe we have capital K users to generalize this. Then we can further kind of make this diagram look a little more organized and just write it like this. So it's just the same diagram as before, where instead of 2 transmitters, I have a generalized number of capital K transmitters. They are simultaneously transmitting, and the corresponding channel matrix is what we have called capital W. There are a total of n antenna elements, and then this reception, which is now a vector, is getting processed by this beamforming engine. And the single user mesh filter technique uses a matrix W as the input to this beamforming. Actually, here, to be consistent with this notation, maybe I should have called this as W conjugate. But that, I think, would disconnect with the notation that we have introduced earlier. So let us still keep on calling this as W. The single user mesh filter is same as W, except what is going on inside this beamformer is that we take W conjugate, or specifically W Hermitian transpose, the complex conjugate transpose of W, and multiply that with the received vector. And as a result, we get the symbol estimates for transmitter 1, transmitter 2, and up to transmitter K. Okay? This is nothing but the extension of this diagram, which is nothing but the extension of this diagram. And that actually is what we have called earlier as this vector Y. If you recall, over here, when we said that we can do this operation and get this sufficient statistic vector Y, that is what we have done. W Hermitian times the output of the array. So this is the question that I had asked you, and I think that the clear answer I didn't get last time, that this vector Y is nothing but the single user mesh filter output. And that is what we are showing by this diagram. Okay. Now, we said that if I look at the equation for Y, that sufficient statistic, if the columns of W are not orthogonal, remember, if the columns of W are orthogonal, then we are done. Then we get back to our CT516 formulations. Basically, the matrix W is orthogonal, and with only some scaling, we can easily make it orthonormal. We are back to CT516 formulation, and this single user mesh filter gives us the best possible estimate that we actually kind of reviewed before we even began this particular lecture topic. We saw that using this single user mesh filter output, when W defines the orthonormal basis, gives us the maximum likelihood, ML estimates, in the Gaussian noise channel. Or with only a small change, we can make it a maximum a posteriori estimate. And so if W happens to be orthonormal, then this is all, we are done. But in case of beamforming, in case of NOMA, this W will not be an orthonormal basis matrix. And therefore, the collection of this symbol estimate that we have called this sufficient statistic vector Y ends up having a formulation which is Y is equal to R times S plus some noise vector. Okay. And so what we have called the correlating detection takes this single user mesh filter and it multiplies that with the inverse of R. And then what we get are decorrelated symbol estimates. We also looked at the MMSE technique, which additionally needs the estimate of signal to noise ratios of all these users. But if we have those, then instead of doing just simple decorrelation, we can do MMSE. Okay, so this is the block diagram schemes to understand what we are doing in context of single user mesh filtering and how that decorrelation or MMSE schemes are just kind of adding kind of a cherry on the top of ice cream. Okay, now I want you to hold this diagram. We are going to kind of almost park this temporarily. What I want to do next is analyze for a very simple case when there are only two transmitters and their corresponding array vectors are not orthogonal. I want to look at what happens if we stop here. What type of performance do we get? Versus what happens if we do decorrelation versus what happens if we do MMSE. So that will kind of give us a little bit sharper insight, more clearer understanding of the benefit that we are getting by putting this additional linear algebraic processing at the output of SUMF. So that is what I would like to connect this slide to. But before that, I want to take kind of what in the previous lectures I would call it the interlude or sort of the intermission, where we are almost kind of changing the topic. This is kind of the main flow that I want to continue, but before I will continue this main flow of discussion where we will start looking at the detailed mathematical analysis of this beamforming single user mesh filter versus decorrelating detector. Before we do that, this kind of also leads us to something which is quite interesting and which is quite relevant. So that is where I'm going to take kind of a kind of chase a trail which is very relevant at this point. So we will kind of pause this. We will take a break here from this continuing flow of discussion, and we will take up something which is quite related because it has a lot of relevance on some of the papers that we are going to be looking at after this. Okay. Oh yeah, and by the way, the reason why I thought of doing this is because just a few days back I was talking to Joel and to Bibin, and I realized that this is something that I have probably not mentioned to you in a whole lot of detail. So I thought it's good to emphasize this particular aspect of beamforming. What you would have probably noticed is that I have put here this signal direction arrow. That I think I should have it on all of the slides. So you see that in all the diagrams that we have seen, the signal is originating at this transmitter and it is getting received and it is getting processed by this antenna array receiver. The transmitter is in this color, the receiver is in this little pinkish color. And the signal direction is transmitter to receiver. But you see that any time that we have this type of receiver, it is usually not a standalone receiver. It also acts as a transmitter, right? I mean, if you think of this array of antenna elements as being on the top of a base station tower that you see all over, I mean, everywhere these days, then that base station tower is not only doing reception, but using the same antennas, the tower is also transmitting the signal towards the same phones, same terminals. And so what we can say is that although we have been looking at this beam forming from a receiver perspective, it actually turns out that these diagrams and even the math actually completely captures what we need to do transmit side beamforming. Okay, so ultimately it boils down to the algebra, and that symbolic math doesn't know what is transmitter, what is receiver. And so what we did here can be directly applied to when the base station is doing the beamforming while it is transmitting. Now, for some reason, in the literature, if you read some papers that we will be looking at now, and maybe what you would investigate on your own, you may find that every time that they are talking about the receiver side processing, they call it beamforming. But when they talk about transmitter side processing, the same algebra, they call it transmitter precoding. The word beamforming became precoding. So that is some convention that is present in the literature. If you don't know that, then you might kind of think that, oh my God, this precoding is something totally new. I don't know what it is. It's confusing and all that. But actually, it's just a fancy word of saying that it is the transmitter which is doing beamforming. Now, one practical aspect is that for the transmitter to be able to do beamforming, it should know that matrix W. A lot of the times that matrix W is being estimated at the user devices. So there has to be some type of feedback mechanism by which the user terminal, the phone or any communication device informs back to the base station this specific channel coefficients. The other aspect is that we are assuming that the transmitter is a central unit, just like what a base station is. So this transmit side pre-coding cannot be done if different users, this capital K users, are not co-located. And the reason for that is what we will see pretty soon. So those are the two practical considerations that we should keep in mind. But with those caveats aside, I can draw the same diagram in an upside down manner or the reversed arrow manner. So now this antenna array has become my transmitter, and all of these devices are now becoming receiver. So that is why I made them to be pink in color, and this is now the color that we had used to denote the transmitter. But otherwise the math remains the same. This particular vector is not the estimated vector, it is instead the symbols that we want to transmit to these different receivers. So this is, let us say, QPSK symbol for receiver 1. This will be, let's say, QAM symbol for receiver 2. This might be some APSK symbol for the kth receiver. So these are the symbols that we want to transmit. One possibility is that we don't do this MMSE or decorrelation at all. We close our eyes to the fact that this matrix R, correlation matrix R, is not the identity matrix. And we just assume that it is the identity matrix. Then all we do is we pass this QPSK, QAM, etc., the symbols to the single user match filter. And then that goes out in the space. That is what we transmit from these different antennas. And so now the direction of these arrows has also reversed. The matrix remains the same as before. All we are saying is that some type of feedback mechanism has been implemented so the transmitter got the knowledge of W. And so now that is all. I mean, that is all there is to it. We did the transmit side beamforming. Additionally, if we do this MMSC or decorrelating step, then we can actually even not only do the beamforming, but we can cancel the interference that otherwise will be there between different end devices. Okay, so in summary, our received vector y is W times S. This is what we have seen earlier. Actually, there is a typo. I should also add here the noise component. So it's WS plus some noise vector U that I forgot to write on this first bullet. So this is our received vector y. S is the vector of symbols that we now want to transmit. Remember, we are talking about transmit side beamforming or transmit precoding. So S is this the vector of symbols that we want to transmit for different end users. If we just transmit S like this, then this received vector Y will be this matrix vector product, and the receiver will be not able to get any beamforming advantage or any interference cancellation advantage if we directly transmit S. But instead of transmitting S, what if we transmit S hat? S hat comes over here. This is what is actually getting radiated by this antenna array. So we are transmitting S hat. And that S hat that we want to transmit is not our original symbol vector S, but it is this S vector S multiplied by this entire matrix. Now we will recognize this matrix as nothing but our decorrelating detection matrix, except we are writing it in a kind of, instead of left to right, we are writing it right to left manner. If we know W, which we have assumed that we know somehow at the transmitter, this is just a linear algebraic operation that the transmitter can perform. And so if we transmit S hat, the received vector will be now WS hat plus noise. If I plug in the expression of S hat, which is here, into this equation, then I get S plus U. So you see that all the interference vanished. I essentially got the same answer that I get from doing the decorrelating detection at the receiver. Except here, these individual receivers don't have to do anything. See, that is the magic. These lines, they are coming over the air to the receivers. And this part here, it is just happening through the propagation mechanism. The receiver is not doing anything whatsoever. It is the transmitter which is doing all of the beamforming operation. The receiver is just happily receiving the symbols, and it receives the symbol as if there is no interference. This vector S is getting received at each of this receiver. Vector Y, remember, is this vector, y1, y2, y3 up to y of k. And what our math tells us is that by doing this pre-coding and beamforming, y1 will be exactly equal to s1, y2 will be exactly equal to s2, and y of k will be exactly equal to s of k. With some noise, but that noise would have been there anyhow. So this is called the transmit side beamforming or transmit pre-coding scheme. The advantage is that all of the signal processing complexity of performing this type of operation has been moved to the transmitter. Your phone doesn't even know that it is actually getting a beam formed and interference cancelled input. Okay, so that is where we will park this little bit of side track that we have engaged in. And now we will go to the receiver performance analysis, which is our the continuation of the topic that we were discussing. Okay, sorry, actually no, let's not do this right away. I wanted to go over a few papers. Okay, so let us actually continue on this side track a little bit more before we start this receiver performance analysis topic. Okay, let me take a break at this point. I'll be back in just a few seconds. Okay, so I'm back. I want to start by asking you whether you have followed one of the objective of one of the papers that we saw last time, which was this hybrid approach of beamforming for massive MIMO systems. We looked at one such paper last time. I have put that paper, I think, on our Google Classroom as well. So if you have not looked at that paper after that lecture session, I think you should take a look at it, because that paper actually does a lot of this direction of arrival estimation. But it does that using this hybrid approach. Do you recall what that hybrid approach is and why it is motivated and so on? Anudeep? Okay. Bhavesh? Do you recall that hybrid DOA estimation, the direction of arrival estimation using the hybrid approach in context of massive MIMO millimeter wave? This was the paper that we looked at last time. Bhavesh, are you there?
Hello.
Yeah.
Yes, sir. Can you repeat, sir? Just the last part. It got missed somewhere.
So last Monday's lecture, I went over a paper which was about hybrid implementation. in the context of the hybrid approach was applied to doing the direction of arrival estimation. But my question is, what was that hybrid approach and why was it motivated?
So the QPSK and the BPSK with 4 BPCU?
No. That is something.
There is one more
This is we are talking about spatial modulation. I'm talking about the DOA estimation paper we looked at last time. Were you there in the last lecture?
So the Monday's lecture, I was not there.
Oh, okay. So fine. Then you wouldn't know. Joel, what about you?
Sir, we like if n is the total number of antennas, we made
Yeah.
m times k. Like we divided into sets of like let's k sets of elements
Correct.
for economical reasons.
Correct. Yeah. So Joel captured the essence of it. It was entirely the motivation was coming purely from the cost-cutting perspective, but it's a major motivation, and that has driven a lot of research into implementing the massive MIMO systems in a economically efficient manner. So there are two objectives. One, massive MIMO is known to give significant performance advantages. Two, you want to get that performance advantage without having to spend your fortune in building the base. And so that becomes the challenge. And the paper that we are now going to look at actually is focusing on the same challenge. In fact, a lot of these papers which are on massive MIMO beamforming or millimeter wave techniques are all trying to solve this challenge. How to maintain the performance advantage that you get if you have a large number of antenna elements. That capital N in our notation is like maybe 100 or 200 or 300, like that. But still we do not end up incurring a very large cost of implementing such an antenna array. Okay, so this paper is written with that perspective. But unlike that DOA estimation paper that we saw last time, now here the objective is to actually do the beamforming. And it is done in both the contexts. You can think of this hybrid approach either getting implemented on the receiver side, then it will be called hybrid beamforming. Or in many papers, this approach is considered as getting implemented in the transmit side. Then it will be called hybrid pre-coding, hybrid transmit side pre-coding. So that is what we will be looking at. But before we do that, in order for me to properly put this discussion in some proper context and also kind of refresh your memory, I want to show to you some of the lecture notes of our CT516 course. So that is what I'll be first projecting here. Okay, so this is some notes directly taken from this course that you took last time, where we said that a modulated signal can be represented in this compact manner, AM times cosine of 2 pi fct plus theta m. And this AM component, the amplitude modulation, is represented by this term, and the phase modulation is represented by this theta term. And we said that this signal can be represented as a linear combination of the basis functions, f1 and f2. And these bases are orthonormal. And one example is that these two bases are cosine and sine functions. And then we can write this S of the modulated transmitted signal as just in a linear algebraic manner. And then at the receiver, and by the way, this linear superposition of basis function is to be thought of as synthesizing the signal. And at the receiver, we do the match filtering part, which actually we just now looked at. And that can be also thought of as the analysis part. And because this basis is orthonormal, the synthesis and analysis are inverses of each other. And so we get the original constellation coordinates back, SM1 and SM2. Okay, so this is what I think you all are familiar with. But then what we said is that this same type of basis function formulations can allow us in general a significant reduction in the signal representations. Okay, so there what we said is that let us say that we have some vector C. It's a two-dimensional vector, and it is oriented at some angle theta with respect to x-axis, and it has some magnitude v1. And so in order to represent this vector, I need two non-zero elements. Cosine of theta is generally non-zero, sine of theta is non-zero also, except when theta is either 0 or 90 degree or so on. Most of the time theta is not like that, and so we need two real valued numbers to represent this vector. But what if I do a basis function transformation? What if I take this C and multiply it by this basis matrix that I have carefully chosen so that this basis function actually rotates the coordinate axis and makes it in alignment with this vector C itself. And we saw that a corresponding basis matrix E would have this cosine theta, sine theta terms. What happens is if we do this type of basis function transformation, then essentially our coordinate axis gets rotated by C, rotated by theta. And so this vector C becomes aligned to the new x-axis, which is the first column of our basis function. It's aligned to this vector E1. And so now with that, our vector V, which is obtained by this transformation, has only one non-zero value. The other value is 0. If I'm doing some data compression, then instead of storing two non-zero values, I have to store only one value. The other I know is going to be 0. You may say, well, what is the big deal? It's becoming quite impressive if this N here is not just 2. It is not, C is not a 2x1 vector, but C is maybe residing in a much higher dimensional space. So suppose if C has 200 elements, and now if by doing this, I get a vector V which has also 200 elements, but I know that only one out of those 200 elements is non-zero, others are 0, then I have done a significant simplification in the data representation. In CT516, when we went over this, our focus was on data compression. Now, our focus is on this millimeter wave hybrid beamforming or hybrid precoding. Now, it turns out that in CT516, if you look at your notes, you will see this also that we said that our basis one choice of basis vector which is doing this orthonormal rotations of the original coordinate axis is represented like this. Column of the basis matrix, and that k is coming into the numerator of this exponent. The denominator is the length of the basis vector, capital N. And so the the kth element of this vector is given by this formula. So E0 is all ones, E1 is like this, and so on. Who can tell me what this basis functions together define?
The filter bank.
Huh?
The filter bank in our case.
Filter bank, yes. But what kind of filter bank? Filter bank can have any type of filters. You can just put any filter in a parallel manner, any different type of filters in parallel manner, and you can have a filter bank.
The DFT.
Sorry, your voice is not very clear.
So all the filters are orthogonal.
And so what did we call them?
The DFT matrix.
Exactly. Correct. So Bhavesh is correct. So this different column vectors together define the DFT matrix. And that is one such basis function which can sometimes, especially if the signal is of this particular nature, this DFT matrix can significantly simplify the signal representation. This C vector is filled with non-zero values. Non-zero values are known to be having this structure, which is the case when it is cosine waveform. But generally, having this structure, then this V will have only two non-zero values, one corresponding to this, another corresponding to that. All the others will be zeros. Okay. Now, I want to ask you one more question, which is this DFT filter bank that Bhavesh just now mentioned. Whenever we talk about DFT, we are thinking of something in time domain. And then we are doing discrete Fourier transform to get the equivalent representation in the frequency domain. So my question to you is whether the same exact DFT concept, can it be applied to the antenna arrays also? What do you think? It makes sense to say that we can do something like DFT for the antenna array output. The antenna array output, if I look at a particular time instant, if I look at all the elements, then they are not function of time. They are function of the antenna index.
Sir, when we will do match filtering for an antenna array, then we get output at only particular frequencies. So we can say they are the function of frequency, like we can relate it like that.
What do you mean by frequency? Remember, when we are considering antenna array, and let's say antenna array beamforming, there is no concept of time as such. There is no concept of time, or in other words, all the outputs of different antennas are collected at the same time. What is the frequency that you are mentioning?
Sir, like frequency is related to the theta angle of arrival.
Yeah.
So
Yeah. Right. So I think Joel is right. So remember, because of that analogy that we have formed between the temporal processing and spatial processing, we can actually do the same type of basis function transformation using exactly the same basis vectors that we have come to recognize as the DFT vectors in the context of time domain processing, in context of temporal processing. We can apply the same matrix capital E, which is the DFT matrix, to the antenna array also. But now if I do that, if I apply the DFT matrix to the output of the antenna array, I can't say that I'm doing discrete Fourier transform as such, or I can still say I'm doing discrete Fourier transform, but I'm not obtaining, discrete Fourier transform allows me to go from time domain to frequency domain. If I do a similar basis function transformation at the output of the array, then I can't say that I'm going from time domain to the frequency domain. So I'm not doing the frequency transformation, but somehow I can still say that I'm doing some type of discrete Fourier spatial transformation, right? I'm transforming from the antenna domain to the space domain, or the DOA domain. Okay, so that is something that I thought I will mention right away. Now with that, let me go to this paper. Not this paper, actually. This paper. So this paper appeared in IEEE Transactions on Antenna and Propagation in July of 2013. The title is Beam Space MIMO for Millimeter Wave Communications. It's actually written by a student, maybe pursuing PhD. Okay, so what this paper is talking about is a continuous aperture phase MIMO. What they're talking about, this continuous aperture, is that it's just a single dish. So it's not actually an array even. It's not those different feed elements, antenna elements that we have been depicting in some of the diagrams. It's just a dish antenna, kind of antenna that you would see on the rooftops and in the terraces. So it's just a dish antenna, and that antenna actually can do just the analog beamforming. There is no discretization going on. But what they are saying is that using that dish antenna, they can somehow do equivalent array formulation, and that is what they are calling discrete lens array. And what they are saying is that if I take that antenna and if I sample If I physically sample the antenna at certain spacing, then it will be as if I have the uniform linear array, 1D linear array, which we have called uniform linear array. The length of the antenna is LT, or in general capital L. And remember, this is actually one physical piece of hardware, only one antenna. So this L is in meters. They are saying that if the waveform that is incoming, it's a narrowband waveform with some wavelength lambda, then although I'm having just one antenna, it is as if I had a uniform linear array with this many elements. And that is what they're calling this critical sampling requirement. Now, this equation 1 should remind you of something. Let's see who has not spoken yet. Arushi? Are you there, Arushi? Looks like Arushi has dropped out for some reason. Komal?
Yes, sir.
Does this equation 1 remind you of something? Even this wording critical sampling also gives you a hint.
Relation between C, lambda, and F.
The length of the antenna, the size of the antenna is L. L is in meters. And this N1D is just a notation for the number of samples that they can get out of this antenna. And that is in the dimension of the space. In our notation, this small n1d will be capital N, the number of feed elements. I'm asking, what can you infer from this equation 1?
Number of samples resembling that linear array, number of linear array that you're talking.
No. Who is next? Kishan?
Sir, like two antennas should be separated by distance lambda by 2, and we are checking how many are there, how many such possibilities.
Yes. How many such possibilities? Well,
I mean, if we divide L by lambda by 2, we can basically say these many can be placed, something
exactly.
like that.
Exactly. Yeah. It is exactly like that. I think maybe what I would put what Kishan is saying in a different manner. If I take this capital L and bring it on this side, it becomes N divided by L. Now, if I consider the ratio capital L divided by N, what do I get? L is the length of the antenna, N is the number of spatial samples that they are bringing out of these antenna. If I divide L by N, what do I get?
Lambda by 2.
No, forget about the right-hand side of the equation. I'm just asking you, if I have some antenna, let us say it is 10-meter long antenna, and I'm effectively sampling the antenna with 10 samples. So 10-meter antenna, and I'm putting 10 samples out. I'm taking 10 samples out of it, and assume that it is uniformly sampled. Then what I get is what?
Per sample 1 meter length until
Basically 10 meters divided by 10 gives me 1 meter. 1 meter.
1 meter per sample.
Sir, Anudeep has answered on the chat.
Oh, he has? Okay. Spacing between each antennas. Yes, exactly. So that spacing between antenna is, we have called it to be small d. And so what this equation tells us is that d is equal to lambda by 2. This is what we have seen in our earlier lectures. That is why they are calling it critical sampling. That as long as I keep the spacing between the individual spatial samples to be lambda by 2, then I will have no spatial aliasing, space domain aliasing. And then therefore I will be able to get effectively this n number of spatial samples. And that n actually will determine the dimensions that I have. It is the dimensionality of the vector x that we have been considering. But here it is being done in the context of an analog system, except the discretization is happening only because we are sampling this dish. In a way, this is kind of falling in the domain of radio frequency design, kind of topics that you would have studied under Professor Sanjay Gupta. But that is the whole RF part of it. The rest of the paper is firmly into the type of discussions that we have been having here. Let us see, what did I want to bring your attention to? Okay, I forget. There was something that I wanted to highlight, but I don't remember it now. So let me move forward.
So,
Yeah.
can we look at this like we have studied Nyquist sampling rate in frequency domain, but applied to time domain, we can say that lambda by 2 is that the Nyquist spatial rate, like something like that.
Yeah. Lambda by 2 would be called the Nyquist rate in the space domain. Okay, but yeah, so good that Joel mentioned this, because somehow I don't know what he said, but that reminded me of this thing that I was not able to remember. In the beamforming literature, there is this terminology called grating blobs. Okay, so in context of phased array beamforming, in context of MIMO designs, this grating lob is a big headache. And always fighting against grating lobs, and designers say that we want to eliminate grating lobs, but sometimes we cannot eliminate grating lobs. So when you again read some wording like this, grating lobs, if you don't know what those grating lobs are, you will be kind of a little bit at a loss. Well, Komal has actually simulated grating lobs. Let me see. Komal, can you, I don't know, is it easy for you to project your screen with that presentation? How much time do we have? 1 hour, 20 minutes, maybe we can take some time. Project that presentation, Komal?
Yes, sir.
So stop projecting and I'll ask Komal to actually present her slides. Yeah. Go down. Yeah, we can see your slides, Komal. You can, please start. Yeah. No. Go at the beginning where you were showing what happens as you reduce the spacing or increase the spacing. Yeah, here. Can you make it full screen? Otherwise, it's fine. So this is where Komal kept d over lambda to be 0.1, and she's getting a particular beam. Now, Komal, show what happens as you increase that. So this is 0.5, 0.7, 0.9, 1, 1.5. Okay, so stop here. So Komal is trying to form a beam in the direction of 30 degrees. But for some reason, she is not able to keep the antenna separation to be equal to 0.5. In fact, it is 3 times as much. Because of that, she's getting aliasing in the space domain. And so when she's forming a beam at 30 degree, the two replicas end up happening at these other angles. These are known as grating lobs. Komal, go to the previous slide. So even with one, there is a grating lob. Go to the previous. With 0.9 also, there is a grating lob. Previous. At 0.7, Komal already started seeing grating lobs. Typically, yeah, so Komal, you are done. Thank you. So typically, the designs are not so bad, like d over lambda becomes 1 or 1.5. But it might become 0.6 or 0.7, like what Komal was showing. And so at that time, you start having these grating lobs, which are kind of along the horizon. You are doing you are suffering from some type of spatial aliasing, but that aliasing is mostly confined to angles which are close to the horizon. Similar to what Komal's diagram was showing at d over lambda of 0.7. If d over lambda is bigger than that, if it is 1 or 1.5, then forget about it. These grating lobs will be everywhere. It will be kind of very close to where you actually want to form the beam. And the worst outcome is that the grating lob ends up being aligned to the interferer, which you want to null out. So what will happen is, instead of nulling out the interference, you'll be actually forming a high gain beam in the direction of interferer unintentionally. And so that is what they're talking about, the compromised security. Some malicious interferer can kind of create some security hazard. But even otherwise, if there is no security issue, there is going to be a lot of interference. And this equation 1 says that, at least in the theory, by making the number of dimension of this, what they're calling cap dish, after it is converted to discrete manner by this discrete lens array, that grating lob concern is not there. Okay. And so with that, the received vector R is Hx plus W, very much like what we have been seeing. The notations are different. This H, we have called it to be W matrix. But otherwise, this is very much analogous to what we have been looking at. Remember, their objective is to do hybrid approach. I don't know whether they have put it here explicitly or not. But let me move forward. So this H is the channel matrix. What they're saying is that what if I actually do H times U, where U is some type of beam forming matrix. And what is U? Okay, so U is formed of this columns U of theta I. So the columns of U are U of theta I. What is U of theta? It is our well-known array vector, which is given by e to the power minus j pi, j2 pi theta I, where theta is given by this formula that we have seen in context of uniform linear array. And they are saying that if the columns of that U matrix are defined for different angles theta, which is 1 over n, then the resulting U theta I are orthogonal to each other. When I have theta equal to 1 over n, I have that, if I consider that sinc function, I am actually sampling the sinc function either at its peak or at its zero values. Because we remember that sinc function zeros are spaced exactly 1 over n apart. That is what this 1 over n is. And when you sample the sinc everywhere at zeros, then you get essentially orthogonal vectors. And so U theta I become orthogonal, but U theta is this particular formulation, and if they are orthogonal, then they become nothing but the discrete Fourier transform matrix, which is what they're calling here. So this is the discrete Fourier transform. Okay, now let us go to their main idea. So this is their cap antenna. Oh, sorry, no. This is the uniform linear array. You see here the feed elements. This diagram is very much like what we have been drawing, except it is turned 90 degree. It is rotated 90 degree. We have been drawing this uniform linear array in a horizontal manner. They have stacked all the antenna elements vertically. And they are saying that with along at the output of each of this element, I need to put RF circuit, RF chain, including A to D converter and D to A converter. Then the output of that goes through the discrete Fourier transform matrix. And then after that, we do some type of digital signal processing in FPGA. So they're saying this is one particular architecture. But this architecture will require so many different RF chains. Plus, it will require this entire uniform linear array. So what they are proposing is that instead of doing that, I will just put a dish. This is one continuous aperture antenna. That is what they're calling the cap MIMO. And this dish, they are going to tap, they are going to sample the dish at multiple points. And that is what they're calling discrete lens array. So the dish output is getting discretized because it is getting sampled. There is no physical set of elements. It's the sampling of the dish is what is giving us the effective result as having the uniform linear array. But what they're saying is that by doing this DFT operation is automatically performed in the analog domain here itself. And so now instead of needing so many different RF circuit at the output of conventional ULA, I need only a few RF circuits. So that is the elegance of their idea. Basically, they are saying that this DLA is going to do the discrete Fourier transformation. And because of the discrete Fourier transformation, what will happen is, if I have only one transmitter or one, instead of having this multiple red colored beams, if I had only one transmitter, by the way, these are the DFT beams that you are looking at in the light gray. And the highlighted red colored gray is where they are saying this DLA will put the discrete Fourier transform beams. So if for some reason, if only one such beam was active, only one transmitter was present, then there will be only one red colored value. And that will appear at the output. And now we have done the match filtering operation directly there and there. And so you need only one RF chain. It is as if over here, I only had one complex exponential. And so by that DLA which performs the DFT, it will give me this vector V, and that vector V will have only one non-zero element. So I don't need so many hardware chains. I need only one hardware chain. In reality, there will not be just one active transmitter. There will be multiple active transmitters. But remember, this is for massive MIMO scenario. the number of elements, capital N, in our notation, is much, much greater than capital K. So suppose N is 256 and K is going to be only 5. Then if I do the conventional ULA, then I will need 256 RF chains. 256 RF chains when I know that at a time only 5 transmitters are active. By doing this spatial DFT using this discrete lens array, they are saying that if I know that at a time there are going to be only 5 active users, I will need only 5 RF chains. I'll still get the same performance benefit that I get by making capital N to be very big. Remember, when N becomes big, a lot of the problems that we have seen earlier, the problem of low resolution, the problem of smearing, even the problem of energy leakage into the side lobes, a lot of the problems go away. Basically, you are able to form very sharp, narrow, focused beams. The width of that sink function becomes pretty narrow, which means that you are able to direct the propagated electromagnetic energy in the direction of interest and remove the interference from all the other directions. That is the advantage of making N to be very large. And that is where the massive word comes into play. Massive MIMO is called massive MIMO because they are making N very large. The problem is that as they make N large, they run into this problem. The cost becomes high because this blue box becomes expensive. So the novelty of this paper is to say that in the analog domain itself, they will perform some discrete Fourier transformation so that they need only as many number of hardware chains as there are number of users. Obviously, you need one RF circuit for one user. You can't have 2 users on the same RF circuit. So even in the conventional systems, this is known. I mean, as there are a number of users, you need as many RF chains. The conventional MIMO was asking for far more many RF chains, which by this discrete Fourier transformation, essentially by zeroing out the elements of C, I mean, zeroing out most of the elements of vector V by performing this DFT, these authors have been able to reduce the RF requirement. So that is a recurrent theme in a lot of these papers. So let me present one more paper, which is actually along the same line. It's in fact written by the same authors. And it is actually expanding on the same theme. It appeared in Globecom 2013. They are showing this beams as they're formed by this DFT-based processing. This is their system equation. And now here, they are applying the precoding. So this is in the context of transmit side beamforming or transmit precoding. Somewhere they should have written it. I can't find it here, but I'll put this paper also on our classroom. Yeah, this is a sentence which implies that they're doing transmit side beamforming. They have k different mobile stations, and they have an access point which is nothing but a base station, and they are considering the model of the received signal at the mobile station. So the mobile station is receiving the signal, which means that the base station or the access point is doing the transmission, which is our diagram with the arrow going from bottom to the up. So this is the transmit side beamforming, and so therefore they are doing transmit side beamforming, which they are calling precoding. And this matrix G, they should have defined it somewhere. Yeah, here. So G can be either match filter, or it can be this decorrelating filter, which they are calling zero forcing, ZF, zero forcing. So for that vector G, the three schemes they are considering is match filter, zero forcing, and Wiener filter, which is nothing but our MMSE. This is the MMSE formulation that we have seen. This is something that, these are the three schemes that we just looked at in the block diagram. So they have that by means of this matrix G. And then this H is the wireless millimeter wave channel. This is happening due to the propagation mechanism. And it is this H which is having a large dimensionality because it's a massive MIMO system. And so again, they do the DFT operation, the same type of ULA model. And by doing the DFT, which they're calling essentially beam space model, again, some fancy term, ultimately all that they're doing is multiplying by this matrix U, which is the discrete Fourier transform matrix. What they are essentially showing is that if they form beams going from -40 to 40 degrees, then only, and they have, let's say, 20 different user terminals, then they are looking at an overall grid which is so huge. But at a time, there will be only few elements which will be non-zero. And so they need, after doing the discrete Fourier transformation like this, they can work with this smaller dimension h of b. Once they do the discrete Fourier transformation of h, most of the elements will become zero, and so they can reduce the dimensionality of h, and therefore in the beamforming part they make use of h of b instead of h, although it is, I mean, here in this formulation they are making use of full h. It's somewhere they are calling, yeah, here they are reducing the dimension, low dimension system, h of b, and therefore g also will be lower dimension. The main objective is to make h to be lower dimension, and so because of that they can reduce the hardware requirements.
Excuse me, sir.
Yeah.
Sir, sorry to interrupt. Sir, we have a lecture at 12.
Okay, so I'll stop here. Maybe I'll take a look at one or two more papers next time before we get into that performance analysis. Okay, so those who have lectures, they can drop out, and I'll soon conclude today's session.
Thank you, sir.
So yeah, So to summarize, what I wanted to kind of bring to your attention is that the topics that we have studied in this course so far are currently being researched on. Okay, so this is like hot off the press. And a lot of these papers, 2 months ago, you would not have been able to read because you would not have necessarily prerequisite to be able to understand these papers. But now, actually, all these papers, which I'll be putting on our Google Classroom, you are very close to fully grasping them. And in fact, once you read the paper, once you connect it with the content of the course, with what you are doing in your lab, you should, the ground will be open to you, the playground will be open to you. You will say that, okay, these guys did this, and they captured it in this paper. The mathematics look kind of daunting, they look intimidating. I would not have been able to easily understand the content of the paper before looking at some of these theories that we have been studying in this course, but now I understand it. The math is just kind of an abstraction. The underlying idea is very simple. And if they can do it, I can do it. I'm sure you will start getting that confidence that the subject matter is easily comprehensible. I have understood the matter. And then the playground is open to me. I can take their idea and run with it. I can do other things. I don't have to be confined by their proposals and their ideas. And so that is what we will be looking at in some of the papers next time. This other paper by Jinyu Gao, it appeared in 2016, is also doing the same thing. Here, this is the DLA. This paper is written by some totally different people, not by the same, this Brady and Sayed. Sayed and Brady came up with this idea, but this Gao and others, they ran with it. They're using the same thing, DLA, DFT, etc. But they put their own spin to it, and they came up with this paper. And Gao, by the way, he didn't write only one paper. He even managed to publish magazine paper, IEEE magazine, where again he's talking about the same thing. He says that instead of having many RF chains, if I have only one RF chain, it kind of reduces the cost. And then, well, one way to do that reduction in cost is to do this DLA. So you see that he kind of, again, landed upon the same idea. As recently as 2019, there is one paper written which also carries forward the same idea of doing hybrid precoding. HB, PBS. PB is the precoding matrix, and HB is that reduced dimensionality matrix after they do the Fourier transformation. Okay, so the message that I want to give to you is that this is what becomes very accessible to you. Once you know the basic concept, suddenly some 5, 7, 10 papers which are on the same topic, you are able to make sense of. And then you will start getting your own ideas as to what you can do to further enhance this hybrid MIMO schemes. Okay, so we will end today's lecture here, and